Good morning and welcome to this next lecture on sound in structural vibration. We were summarizing radiation from a rectangular panel in a baffle, and we were talking of the work by C.E. Wallace in plotting radiation resistance of modes. Okay, so let me add to that. That work is largely numerical. Okay, that means compute Rayleigh integral, then from there you compute intensity, and then you compute power over a hemisphere, and then you compute radiation efficiency or radiation resistance. It's numerical. However, at low frequencies, as I have mentioned before, he has given approximate radiation resistance expressions formula, which we have seen for an odd mode earlier. Okay. The next, or rather the main key work in this area, which actually should be mentioned earlier, I suppose, is by G. Majdanek. Okay. So there is a 1962 key paper published in Journal of Acoustical Society of America. Title is something like ribbed panel radiation efficiency or sound radiation. I'll give you the exact title maybe next time. Okay, if you type this in Google Scholar, you'll immediately get it. Okay, so this is a very key paper. So there also a power integral is formulated, acoustic power integral is formulated, okay, in a very different manner, so that it's convenient for approximations, closed form approximations. Okay, some special relations are used, and then for radiation efficiency, approximate closed form formulas are presented. For various frequency ranges. Okay, for example, whereas Wallace does a numerics over this, okay, so Majdanek does an asymptotic expression for this range, some more other expression for this range, some expression for that range, something for this range here, and finally close to coincidence and beyond. So in local frequency regimes, he finds approximate formulas. Okay, and more importantly, he classifies modes. As corner radiators, as edge radiators, either X edge radiator or Z edge radiator or double edge radiator or acoustically fast. He classifies the modes in this manner and explains the cancellation. Okay. For example, many cases arise beyond what I have spoken here. For odd modes, you get all of them radiating in a same sign, but if you have even modes, you could have different sign at the corners. This, okay, at the corners you could have a different, because even mode is like this. This is an even mode. okay. P equal to 2 looks like this, P equal to 2 is even, it looks like this. So it's negative on one side, positive on the other side. So if you look at cancellations, at the edge you will have one sign for the right side, one sign for the left side. So you could have opposite signs, okay. Now further things arise if these opposite signs sit close together. If they are close together, they nearly cancel each other, whereas if they are a little bit apart, then cancellation is lesser. So these additional finer cases arise, and he discusses all these cases and the related radiation efficiency formulas for all the cases, okay. Now finally what he does is that realistic radiation involves all the modes at a certain frequency. It's not modal, okay. It's not you that you fix the amplitude and talk of cancellation, or you know don't worry about cancellation but worry about resonance. It's not that. So realistic radiation is all the modes are radiating together. So if we look at the AB quarter circle where the modes are sitting, okay, then you will have and your, let's say your acoustic circle is here, acoustic circle is somewhere here, then this is the bounds of acoustic circle, okay. And then so on this KB he assumes that this line is studded with modes, not as discrete points as we saw earlier, not as discrete points, but a distribution of continuous distribution of modes with equal energies, okay. Then he computes radiation efficiencies for each of these regions, okay, because these modes will be Z edge, these modes will be X edge, and these modes will be corner and so forth. So he separately computes radiation resistance or efficiency for each of the regions. Let's say 1, 2 and 3, and comes up with what is called a modal average radiation efficiency. Okay. So this gives a picture of a panel radiating with all its modes in some average sense. Okay. So the idealized modal average radiation efficiency in some non-dimensionalized coordinate looks like this. Okay. Now along these lines there have been papers written. One is by N. Thompson in Journal of Sound and Vibration in the year 2005, and it is somewhat titled like this: the radiation efficiency of baffled plates and strips. And there is another also relevant by Lie and Gibelling in JSV year 2000, which is somewhat titled Determination of the Radiation Resistance of a rectangular plate, something like that. These are relevant papers about which, if I have time, I will make some comments later. Now I want to do one thing here which is not correct, which is 3-1 is an odd mode and 1-2 is a odd even mode. So 3-1 looks more like this and 1-2 looks more like this. 1-2 is more inefficient than 3-1. There's more cancellation. So that is, we model now. We will model a radiating panel, a sound radiating panel, of course placed in a baffle using monopoles. Monopoles. What do we mean by that? What we mean is that there is this panel let me say it's currently vibrating. Let me draw it first. 1, 2, 3, 4, 5, 6 and make it 7. Okay, so 1, 2, 3, 4. So this is 4 and 1, 2, 3, 4, 5, 6, 4 by 7 mode. So we'll say M1 is 4, N1 is equal to 7. Okay, so in this case I am changing the coordinates a little. I will take this as x, this as y. Okay, and this whole panel now has dimension b, capital B in this direction, and this whole panel has capital A in this direction. Okay, so now individual cells are radiating. These are cells, okay, model phase cells. So we'll call this a phase cell. Why? Because one is in plus, one is minus, one is plus, one is minus. The whole cell is in one phase. Further, this will be minus, plus, minus, plus, and so forth. Okay, so each of these is called a phase cell. Okay, now if we make the assumption, that a phase cell satisfies a monopole condition, okay, then we can use monopole formulas. So then what we can use monopole formulas. And once you use monopole formula, it's more of a summation than an integral. Okay, you sum all the monopoles. Okay, then you might get some additional insight. That's of course the main point here, additional insight into panel radiation. Okay, that means we have to satisfy a criterion that this phase cell is a monopole. Okay, so mainly phase, so as long as that is correct, we will have accurate results. Phase cell must be a monopole. So now how to set a criterion? So we have the dimension of the panel is A, capital A and capital B. Okay, so the phase cell dimensions are A over M1 and B over N1, which means the cell area, phase cell area is given by AB. Okay, well, let's see. A is equal to A over M1, B is equal to B over N1, and phase cell area is equal to AB. Okay. Now, of course, the acoustic wavelength lambda must be greater than something, some cell dimension. Okay, something related to the cell for it to be a monopole. That leads to a monopole definition. Okay, so if we look at some corner region of the panel, let's say this is the corner and this is one cell and this is the next cell, this is the next cell in the column, next cell, this is plus, this is minus, minus is plus. So then a wavelength in this direction is this, wavelength in the x direction is this, and a wavelength in the y direction is this. Okay, and so one diagonal dimension is what? One diagonal dimension is twice, square root a square plus b square. This is one diagonal dimension. Okay, so if we want to make lambda bigger than some wavelength or some wavelength like dimension, so it has to be greater than this, it has to be greater than this in the x direction, that in the y direction. So we make lambda greater than twice the diagonal. Okay, so this is the diagonal, we make it bigger than twice the diagonal. Okay, it's a good enough measure. We are doing an approximation, so it's a good measure to do that. Okay, that means what happens now? What happens is that lambda is greater than twice square root of a square plus b square, which is a by m1 squared plus b by n1 squared. Okay, and lambda is what? How is it related to wavelength? Lambda. Okay, so we have twice pi by k, okay, greater than twice square root of a square plus b square. Okay, so that means the acoustic wave number k has to be less than this pi by square root of a square plus b square for a phase cell, for a phase cell to behave like a monopole in that mode alone, in that mode. That's important. Okay, so again we are looking at modal radiation, we are looking at a single mode radiation. single mode radiation. Okay. So now we chose a dimension A cross B, a panel of this dimension. It's a square panel. Okay, meter square. And let's just see some values of this lambda and k and how they satisfy. So the mode M1 N1 mode, okay, and we have gamma, okay, which is of course k by square root of m1 pi by a whole squared plus n1 pi by b whole squared. This is gamma. Then we have lambda, which should be greater than some value. Then we have acoustic wave number, which should be less than some value. Okay. So if we look at the 1-1 mode, 1-1 mode for this particular panel, okay, in air, okay, we will find that lambda has to be greater than 0.92 meters. Okay, if lambda is bigger than that many meters, then a single cell will be a monopole. Okay, because 1-1 means the whole panel is a cell actually, right? There is no nodal lines. Okay, so the lambda is also quite big. Okay, then k the has omega over c, so it has to be low frequency. Okay, so it has to be less than 6.81. We are doing this for air. Okay, and the kp value, the modal wave number value is 13.62. Okay, this is modal. Let's call it k m1n1, let's say m1n1, not confused with the infinite panel. Okay, similarly if we do m1 2 n1 is 1, so this gamma is 0.5 about. Then themselves the cells have become shorter. Okay, and therefore what happens is lambda has to be only greater than 0.72. Okay, so now the wave number can be higher, frequency can be a little bit higher, so it comes to 8.6, and this of course is 21.54 here. Okay, and similarly if we go down, we look at m1 is 5, n1 is 1. Okay, here the lambda has to be bigger than 0.66, k has to be less than 9.45, this is 49.14, gamma starts to go down. Okay, now we can put a further refinement on this. We can put a further refinement on this, which is what? This is one cell. Okay, this is not a whole plate, this is one cell. We can further divide this into pieces equally in the x and y direction. So in this case we have broken into 3 by 3, which is 9 more cells. Okay, we have broken it. So if we do that, then the criterion is that the subcell is a monopole. The subcell is a monopole. So we have refined it. Okay, the definition is now refined. So we should get better results. So what that does is that lambda, so we'll call it lambda 3 is to be greater than 0.3, right, because the subcell is smaller, lambda restriction is smaller. So K3, the related acoustic wave number, has to be less than 20.44. For 2-1 mode, lambda has to be greater than only 0.24, and here only 0.22, and K3 has to be less than 25.85, 28.35, etc. Okay. So now let us see, we will do some mathematics. Okay, so let me redraw here. We will specifically look at 4-7 mode just for being specific. It is more demonstrative. So 1, 2, 3, 4, 5, 6. I always fall short here. 7. Okay, the 4/7 mode. 4/7 mode. Okay, so let us look at the volume velocity. So what is it? V tilde PQ or VW. Let's VW. VW. We have chosen somehow the symbol VW sine M1 pi x by A sine N1 pi y by B. That is the mode. M1 is 4, N1 is 7. That is the mode. Okay. So the volume velocity now, what is the volume velocity? Q is equal to integral 0 to A, small a mind you, integral 0 to B, small b. Okay. So VW sine M1 pi x by A sine N1 pi y by B dx dy. Okay. So let me continue here. This is equal to VW A by M1 pi B by N1 pi cos M1 pi x by A with limits 0 and A by M1 cos N1 pi y by B with limits 0 and B over N1. So this gives me VW 4AB by M1 N1 pi square. This is the volume velocity from a single cell, single phase cell. Okay. So now in trying to approximate using monopoles, which will lead to summations and not so much as integrals, and still trying to see if a cell is a monopole. Cell is not always a monopole, some frequency it will fail. Okay. So the smaller and smaller cell you take, better you are. So first idea is we want a volume velocity which is uniform across the cell. Okay, if this is a cell, we want uniform velocity on the cell. Okay, that should equal the volume velocity here. Okay, so what does this mean? The velocity which is uniform into A by M1 into B by N1 should be equal to this VW for AB by M1 N1 pi square. So if you cancel this off, there is a correction. Vm value is Vw into 4 by pi square. Okay. Now there is a further refinement possible, which I will only mention but not go through details. Further refinement possible, which is we break this phase cell originally into subcells. We break it into further subcells, 3 by 3, 4 by 4, 5 by 5 and so forth, further subcells. Now that subcell will be a monopole, which is easier because as it is, its dimension is small. Okay. So making subcells equal subcells, so D subcells in any direction, so D cross D. Okay. So if D is 3, then we have 9 subcells. Okay. This gives better results. Okay. There is even a further refinement if you actually look at a mode. Okay. So it will be like this in one direction, whereas it's like this in the other direction, you know, etc. It has this shape across the plate. Okay. So if a cell happens to be sitting somewhere here, a cell is sitting here, okay, then and again it is divided into subcells. Okay. So if I explode that small region, that is a phase cell to begin with, but within that there are subcells now, then each subcell is seeing a different amplitude. Each subcell is seeing a different amplitude. Okay. So if I accommodate the amplitude change, not make it uniform. Okay. Give this cell an amplitude appropriate for its volume velocity, give this subcell an amplitude appropriate for its velocity and so forth, then I will get a much better refinement. Much better refinement. Okay. So one is breaking into subcells, the other is amplitude attributing appropriate amplitudes. I will get a much better refinement, and I will get a, so what are we trying to do? We are trying to find radiation efficiency, right? Radiation efficiency. So we will get curves as good as Wallace till the coincidence frequency. Okay. So now time is up, okay, for this lecture. So I will close here and continue from the next class.